All right, welcome to the start of chapter 7, which focuses on covalent bonding. So we've talked pretty extensively now, um, especially with respect to electron configuration, about how and why ionic bonds form based on the octet rule. And we know that the difference between an ionic bond and a covalent bond is ionic bonds are typically metal and non-metal. The metal will give up an electron or ionize, and the non-metal will accept that electron, and then we'll have an unshared um, electron uh, relationship, which leads to an electrostatic interaction, that positive and negative bond. So covalent bond, though, we haven't really talked about very much yet, but that's where we have a nonmetal and a nonmetal in the periodic table, and those two share electrons jointly between them. And so I've got this image down here from your textbook, which just shows two um, hydrogen atoms, or really it could be anything, but they're likely hydrogen atoms here, and they represent the two types of forces that atoms would experience when they form a covalent bond. So in a covalent bond, you've got these two atoms that they're coming together, right? And as they're pushing themselves together, they're experiencing these two forces. The first of which is you've got this big positive nuclear charge right in the center. So bringing like charges together, if you've ever brought the two similar ends of magnets together, there's going to be that repulsive force, right? They're going to push each other away. But at the exact same time, you've got these negative clouds of electrons that surround the nucleus, and there's going to be an attractive force between the negative electron of one atom and the nucleus of another, and vice versa. And overall, in a covalent bond, for a covalent bond to form, that attractive force has to be greater than that repulsive force. And so if that's true, if attraction is greater than repulsion, then we get a covalent bond to form, in which case we can have electrons being shared between two nuclei or two atoms. So when we're thinking about that hypothetical situation, so let's imagine you've got two atoms in space. Again, these are hydrogen atoms, and let's say they're infinitely far away from each other. Let's look at that in terms of the energy and sort of the balance of these attractive and repulsive forces. So what I've got on the right side over here is this figure that represents energy on this y-axis and internuclear distance increasing to the right. Internuclear distance is going to be the distance between the nuclei of the two atoms. And so out here we've got this infinite distance, which is how we're sort of setting it up to begin with. So let's imagine we've got two hydrogen atoms. They're infinitely far away from each other. They're on the opposite sides of the room. And then let's imagine hypothetically what happens as we slowly push these things together, which means we're traversing this line on the figure. At some point, they're too far away. When they're too far away from each other, they're just independent atoms and there's no bond. So no bond is formed, and if we look at the energy is 0, which means it's the same as what the hydrogen atoms would be by themselves. So 0 refers to essentially that starting point. No bond form, they're just the energy of the individual atoms. As we keep pushing these things closer and closer and closer together, we start to have sort of the interaction of the attractive forces, because the first thing that those atoms are going to encounter with each other are their electron clouds. And so they get closer and closer and closer, and we start to see a net decrease in energy. And remember from our previous chapter that decrease in energy is a net stabilization of the universe, of that molecule, right? We want to go from high energy to low energy. That's how bonds form. That's more stable. And so what we see is that the hydrogen atoms that were individually separated from each other, they get to be more and more stable as they traverse down this red curve until they reach sort of a minima. And that minima right here, what do you think that minima refers to? Well, that's the actual bond length. That's the perfect length that separates the two nuclei until we start to go back uphill in this case. And if we start to go back uphill, what we're doing is getting these atoms too close to each other now. And the too close proximity here starts to invoke this repulsive force where the nuclei are just getting too close, and now the energy of the system starts going up, and then at some point it crosses where the individual atoms are, and at that point the stability of the molecule is no different than the stability of the atoms themselves, which and then there's no driving force for the formation of that thing because the energy is the same, so it might as well just exist as atoms. And at some point you get these things way too close to each other, and it actually takes energy to get these things that close. And in other words, if you let go of them, they would just bounce back to their original state, which would be right here. So the sort of ideal distance here is where the balance of forces are minimized, meaning that you get the maximum attractive force in the minimum repulsive force. That's going to set the minimum energy of the system, which also sets the minimum distance here. That distance is going to be the bond length. That's what we would measure experimentally in a covalent bond.